The next slide goes into a background and theory of why are we interested in rubidium as an alkali or a vapor for our gain cell, and also the type of problems we run into with using alkali, rubidium-induced glass, and DPAL failure mechanisms. So rubidium has atomic number 37, atomic mass of 85, and it's a soft silvery white metal, easily vaporized, melts at 39.3 degrees Celsius, has a convenient spectral absorption range. Typically we're looking for 780 to 900 nanometer for a DPAL application. It makes it a frequent target for laser manipulation of atoms because of the convenient spectral absorption range. It's typically used in glass envelopes of DPAL gain cells. It can also be used in glass envelopes of rubidium discharge lamps, a critical component widely used, rubidium gas cell atomic frequency standard for nav star and GPS satellites, rubidium diode laser coolant and the Bose-Einstein condensate, spin exchange relaxation free magnetometers. And so the biggest concern is that the rubidium vapor reacts with the glass envelope to reduce both the reliability and the lifetime of the rubidium gain cell in DPALs, already evidenced by Volk et al. Reference there in rubidium discharge lamps. This work was done at the Aerospace Corporation. The next slide, we continue with the rubidium-induced glass and DPAL failure mechanisms. Thinking of the reaction of a gas with a quiescent liquid, according to the kinetic theory from Don Wickert's, the assumption is that glass is simply a liquid with high viscosity, no glass saturation effects. Diffusion occurs in the condensed phase, arbitrary thin surface layer of the condensed phase engenders law equilibrium with a partial pressure of the rubidium vapor. And so this turns out to be a useful analogy for reaction kinetics across a phase boundary, and it also allows the prediction of consumption versus time as a function of temperature, which is a lot of work that the Volk people, Volk's at Aerospace Corporation was engaged in and published. Two damage mechanisms for glass are identified. The chemical reaction requires high activation energy and high temperature. Number two, rubidium diffusion in glasses, and both of those are known to be the dominant mechanisms for damage to glass in contact with rubidium vapor. The overall transfer of rubidium vapor across the phase boundary is actually governed by diffusion into and reaction with the condensed phase. Theory predicts the amount of rubidium consumed is some rapid reactive loss constant of rubidium plus the experimental reaction constant and the screwed at the time, times the screwed at the time in hours. So rubidium is lost through gradual diffusion mechanism, and essentially the major metallic rubidium loss mechanism in diffusion is diffusion into the gain cell walls over time, determined by Volk. We continue on the next slide with rubidium glass systems from Volk again, and it gives basically a relationship between the penetration depth of rubidium, the exposure time T, and the initial concentration of rubidium at the wall. And it's basically the ratio of the penetrated rubidium over the initial rubidium is the other function of the concentration, the penetration depth divided by the square root of 4 times the diffusion coefficient times time. And so from experiment for both high and low temperature, the diffusion constant through silica for rubidium is typically of the order of 3 times 10 to the minus 14 centimeter squared per second. And using a secondary ion mass spectroscopy, or SIMS, C.H. Vogt determined that the rubidium had diffused to beyond 2 micron of the surface region. And what this shows is that diffusion is the dominant loss mechanism for rubidium atoms in a rubidium glass envelope. So the next slide shows rubidium-induced glass and depot failure mechanism, essentially a model of rubidium absorption in cellular glass. After ionization, the rubidium ion plus an electron is produced. The rubidium ion gets incorporated into the silicon dioxide crystal. You have O- ion vacancies are generated because of the excess rubidium vacancies. They capture the available E- or electron, neutralizing and forming an F center, or Faber center, color center. That is, the electrons released in this process diffuse to occupy the vacant spaces. Rubidium atoms present in the vapor penetrates or diffuse into the glass network. You break a bridging silicon-oxygen bond. The electrons get released, orbits around the negative ion vacancy, where rubidium ion reside in interstitial position. There are other theories that suggest a reduction of silicon dioxide to silicon and silicon oxide from the rubidium attack, and that's from Sturzik around 1979. And as you can see, the process described. Next slide. On the formation of color centers can lead to a shift in the optical absorption wavelength, changing the absorption profile of the glasses. That's from Salmoneva et al. We understand how that can be possible because you change the lattice parameter dynamics, and hence the ability to for the wavelength shift to occur. Change in the glass coloration is shown in the figure below, which essentially there is browning of the deep Hal gain cell emulator. In this case, this is quartz, and due to atomic rubidium diffusion. The next slide shows reaction of rubidium with impurities, and potential reactions include reaction with, in the presence of humidity, rubidium reacting with water to produce rubidium oxide, and hydrogen, rubidium with oxygen to produce rubidium oxide. And we show that deposits of rubidium oxide after cooling, after 7 days of exposure at 200 degrees Celsius of the atomic rubidium, cooling back to room temperature, you can see pellets of rubidium oxide being formed. The next slide shows a bit of background and theory concerning 3-level pumping of atomic rubidium. From the lambda pump is the pump wavelength of the diode laser. It excites the electron up to a higher energy state, the 5 p 3/2 orbital. Then it quickly relaxes down to the 5/2 p 1/2 orbital, and from there the next level it goes down to is back to the ground state at 5s 1/2 at 795 nanometer, with a slight energy change, what we call a quantum defect, which is at 2%, and so very extremely low quantum defect. This is per Prospracher, Hostutler, AFRL. The next slide gives an explanation of 3-level pumping of the atomic rubidium, an explanation of terms. S and P represents atomic suborbital 0 and 1 respectively, n equal 2 represents a particular quantum number shell of the rubidium atom. 5 refers to the fifth electron orbital shell. 1/2, 3/2 represents total angular momentum quantum numbers, which is a combination of the L plus S, where L equal n minus 1 and S equal plus or minus 1/2 spin. Delta E represents difference in energy levels. The pump input laser frequency is 3.84 times 10 to the 14 hertz. That for the laser output is 3.771 times 10 to the 14 hertz, which translates to input pump laser wavelengths of 780 nanometer and output laser wavelength of 795 nanometer.